Hi everybody. Uh, I'm Reshma Raj from Civil Engineering Department from SNS College of Technology. Discussed regarding the introduction of earthquake in the previous video. Here in this video, I'm going to explain about the earthquake resistant design principles. Uh, Here I'm going to explain about the seismic performance of buildings. In that I could able to tell like why buildings fail during earthquake. So buildings are actually earthquake doesn't kill people, but buildings do when they fail. There are several reasons why structure will behave poorly under the earthquake forces. One such reason is ductile lack of ductility. Brittle structures crack and collapse suddenly without the ability to deform and absorb energy. So the buildings becomes very unsafe. Next is poor construction quality. Improper concrete mix, inadequate curing or like unskillable workmanship and low quality material severely reduced seismic strength. Next is weak connections. Weak connections like especially at beam column joints, which are the heart of the building's frame. And if these joints fail, even strong beams and columns cannot save the structure. And next is heavy mass concrete at certain floors. When large loads are concentrated suddenly on one floor, like service floors, storage floors, or like heavy rooftop tanks, it increases seismic forces dramatically. And next is non-structured failures. Non-structured failures like walls, parapets, cladding, then ceilings, then it can make collapse that can injure people even if the structure will survive. So these elements must be properly anchored. So in summary, I can able to talk like earthquake performance depends on not only on design but also the execution quality and detailing of the work that we are doing. Next important thing I have to talk about is building under dynamic loads. Earthquake are different from normal loads because the forces reverse direction repeatedly happening. So it will push pull cycle is repeatedly happening over in this earthquake forces. So buildings undergo lateral drift, rocking, and sometimes kind of a torsion it can occur. So the response of the structure, it mainly response of the structure mainly causes on the mass of the structure, stiffness of the structure, damping, and also the nature of the period of vibration. So mismatch between the building's natural period and ground motion frequency can lead to resonance, which is extremely dangerous. If the earthquake happening is for so long, this resonance may occur in the buildings. Next is floating columns, which is a kind of a serious danger. A floating column is one of that stops at an intermediate floor instead of reaching the foundation. The column which does not reach the foundation termed as floating columns. So the load transfers through beams, making the system unstable. During an earthquake, the beams carrying the load can fail suddenly. So these floating columns must be avoided in all seismic zones. So many past earthquakes collapses are linked to this one design mistake of floating columns. Next is the structural configuration. So plan and vertical irregularities may occur. The shape and layout of a building greatly influence its seismic behavior. So a plan irregularity. So what is plan irregularity? Asymmetrical shapes like L, T, U cause uneven twisting or torsion when mass is unevenly distributed and stress is concentrated at the re-entrant corners. Next is vertical irregularity. Sudden it can suddenly change the stiffness or like mass between floors, which create a very weak links. So one kind of example is setbacks, uneven columns and open ground. Next is soft story. What is soft story? This is common buildings with ground flooring is parking. So ground flooring, if it is parking, means it contains very low stiffness, and the upper floor contains high stiffness because of the volume of people living out there. We are building the structure or designing the architectural structure is like that. Next is during an earthquake, the ground floor sways excessively. Sways means it will move or deflection excessively and collapse. So soft storage failure is one of the most common collapse mechanism. If you want to do the ground basement as a, I mean ground floor as parking, better do it in the basement area. So next is that load path redundancy. So proper load path redundancy, why I can able to tell you is earthquake forces must travel safely through the entire structure system. From slab to beam, beam to column, column to foundation, foundation to soil. If any one link in this chain fails, so the entire building will be at a risk. So a continuous load path is the backbone of the seismic safety. If the forces is quietly going through the slab, beam, column, foundation, soil, then no problem. Next, having the multiple load path. Redundancy means the building has backup pathways for force transfer. So even if one element failed, the load will be redistributed and relocated to and go having their own formation of going the releasing the energy from slab to foundation. This prevents progressive collapse, such as redundancy increases overall reliability during the severe shaking. So next is like ductility requirements. Such ductility is explained in IS 13920. And what is ductility? Ductility is nothing. It's an ability of a structure to deform without sudden collapse. So how it saves lives? Allows the building to bend and sway without breaking, provides early warnings before collapsing, and gives sufficient time for occupants to escape, and ensures a life safety design philosophy. So IS 13920, it will detailedly explain how to design the ductile detailing, uh, explain the ductile detailing very elaborately. So India's code that mandatorily needs something is special confining requirements in columns it's needed, and ductile detailing in beams is needed. Strong column, weak beam philosophy is needed, and closely spaced stirrups are very important in seismic zones, and proper anchorage and lap length are very important. So ductile detailing transform a building from collapse prone to earthquake resistant actually. Next, I could talk about the foundation consideration. So foundation, if we talk about the foundation, we have to talk about the soil structure interaction. Soil kind of like that significantly affects the building response. Flexible soil amplify seismic energy. Foundation design must consider soil behavior to our settlement or like tilting. Shallow or like deep foundation. Shallow foundation like footings and roughs suitable for firm soils. Deep foundation like piles needed for weak or liquefiable soils. Proper foundation choices is very essential during in the seismic prone areas. Next is uh, designing for liquefaction resistance. Avoid building on loose saturated sands, we always know, and prefer pile foundation, we always know. Next is lateral force resisting system. Uh, Lateral force means shear walls, braced frames, and moment frames. Shear walls contains reinforced concrete walls that have been high stiffness and high strength, which is very ideal for high-rise buildings and also greatly reduce sway. While the braced frames are very important. Actually, steel braces mainly in X, V, or K in shapes, and it will also reduce the lateral displacement, and it is commonly used in uh, industry buildings, and very economical and very effective also. And next is moment resisting frames. So moment resisting frames are like beam column joints resist bending moments, and it is very architectural flexibility kind of a design it is. And ductile design it requires. So we should follow IS code 13920, and it is very suitable for medium to high rise building. So a combination of these systems create a robust or seismic resistant building. So we can conclude that earthquake performance depends on the ductility, construction quality, and detailing. Irregularities in plan we have to take care of, and continuous load path we have to take care of. In that redundancy we have to ensure the stability, and the soil foundation liquefaction plays a very important role. And systems like shear wall, braced frames, and moment frames, everything is very important, we have to take care of it. So by integrating these principles we can design the building at the protecting and protecting lives even during the very strong earthquakes also. That's it. So thank you for watching. Thank you.